And now for a brief history of instruction set architectures and how architectures have changed over time. The instruction set architecture, or ISA, is the specification that defines what instructions an architecture must be able to implement and how those instructions should be formatted. We use ISAs so that we can write and compile code without knowing the details about how our architectures are implemented. Code that is compiled and assembled for one processor using a given ISA will run on all processors that also use the same ISA. This type of abstraction is invaluable for improving the portability of our code. Additionally, hardware designers can focus on improving performance without worrying about how changes will affect programmers. While the concept of an ISA seems obviously desirable, early computers didn't have them. They had instruction sets, sure, but not instruction set architectures. Each processor had a unique instruction set. This made sense because hardware designers were continually learning how to create new types of instructions, such as floating point hardware. With early computers, you always wanted your users to have access to the latest and greatest instructions. However, because the instructions on each architecture were constantly changing, software had to be rewritten for each new architecture. Consequently, customers were reluctant to upgrade their hardware because it meant that they would need to rewrite their software as well. In the 1960s, IBM realized that this was a bad business model and created the first family of architectures, or ISA. Customers could then choose to buy processors that had varying levels of performance at varying levels of cost. People who needed higher performance could shell out bigger bucks to get that performance, but all processors could run the same software. This cross-processor compatibility incentivized customers to upgrade their systems more regularly. Early programmers worked primarily with assembly language because compilers were still immature and created inefficient code. Since the number of bugs in codes goes up as the number of lines of code are written, hardware designers created increasingly complex instruction sets that could reduce the number of lines of assembly that would be needed. These architectures are called complex instruction set computers, or CISC. Early CISC architectures used rather straightforward machine implementations, similar to the single-cycle architecture that we've learned so far in class. Performance was improved primarily by improving the ability of the programmer to write good code and increasing the complexity of what could be calculated in a single cycle. In the 1980s, a new architecture paradigm arose in response to the increased use of high-level languages and compilers that could create efficient assembly code. Since programmers were now using high-level languages, the most complex instructions on CISC systems no longer provided the benefits that they used to. Reduced instruction set computers, or RISC architectures, use fewer and simpler instructions, and emphasize using techniques such as pipelining and high clock frequencies to increase performance. It turns out that focusing on high clock speeds is a great marketing tool, as customers are more likely to buy processors that have higher clock speeds, even if there isn't an improvement in performance. So, in short, CISC architectures such as x86 have powerful yet complicated instructions that are meant to make the programmer's life easier. However, with increasingly powerful high-level languages and compilers and techniques like pipelining, RISC architectures could make the life of hardware designers easier without hindering programmers. As it turns out, most modern CISC architectures like x86 and x64 are implemented using a lot of RISC techniques, essentially treating their complex instructions as a front end with a RISC machine in the back end. As a quick side note, the MIPS architecture that we are teaching in this class was one of the first RISC architectures. Along with other RISC architectures, most notably ARM, these processors are generally easier to understand and easier to teach. Despite many of the advantages that RISC architectures provide, it turns out that as long as companies like Intel can keep hiring good engineers, we can create RISC and CISC architectures that use pretty much the same techniques to improve performance. Sure, implementing some of these techniques can be harder in CISC, but if you own enough market share and employ enough smart people, that really doesn't matter. As IBM discovered back in the 1960s, customers like to stick with processors that can run their old programs. Therefore, the ISA compatibility of sticking with x86 or x64 on personal computers generally outweighs the potential benefits of switching to RISC architectures. This paradigm may be shifting, though, as mobile computing devices and embedded processors become more common. RISC architectures can generally run on lower power, which is why most smartphones use the RISC architecture ARM rather than the CISC processors in personal computers. Finally, while these topics are well beyond the scope of this course and lecture, we are continuing to improve performance by increasingly using techniques that allow computations to be done in parallel. The 2000s saw the wide adoption of multi-core processors and the use of multithreading to perform multiple calculations at the same time.